Em nome de Alá, o Misericordioso, o Misericordiador.
وهو الذي أرسل الرياح بشرا بين يدي رحمته وأنزلنا من السماء ماء طهورا.
E ele é quem envia o vento como alviçareiro adiante de sua misericórdia, e do céu fazemos descer água pura.
لنحيي به بلدة ميتا ونسقيه مما خلقنا أنعاما وأناسيا كثيرا.
Para com ela vivificar uma plaga morta e darmos de beber dentre o que criamos a muitos rebanhos e humanos.
وَلَقَدْ صَرَّفْنَاهُ بَيْنَهُمْ لِيَذَّكَّرُوا فَأَبَى أَكْثَرُ النَّاسِ إِلَّا كُفُورًا.
E com efeito, repartimos-la entre eles para meditarem. Então, a maioria dos homens a tudo recusou, exceto a ingratidão.
وَلَوْ شِئْنَا لَبَعَثْنَا فِي كُلِّ قَرْيَةٍ نَذِيرًا.
E se quiséssemos, haveríamos enviado a cada cidade um admoestador.
فَلَا تُطِعِ الْكَافِرِينَ وَجَاهِدْهُمْ بِهِ جِهَادًا كَبِيرًا.
Então não obedeças aos renegadores da fé, Muhammad, e com ele luta contra eles vigorosamente.
وَهُوَ الَّذِي مَرَجَ الْبَحْرَيْنِ هَذَا عَذْبٌ فُرَاتٌ وَهَذَا مِلْحٌ أُجَاجٌ وَجَعَلَ بَيْنَهُمَا بَرْزَخًا وَحِجْرًا مَحْجُورًا.
E ele é quem desenliou os dois mares. Este é doce, sápido, e aquele é salso, amargo, e fez entre ambos uma barreira e terminante proibição de sua mescla.
وهو الذي خلق من الماء بشرا فجعله نسبا وصهرا وكان ربك قديرا.
E ele é quem cria da água um ser humano e faz dele parentes sanguíneos e parentes afins, e teu Senhor é onipotente.
My journey into the science of the medieval Islamic world will take me through Syria, Iran, and North Africa. I started in the back streets of the Egyptian capital, Cairo, with the realization that the language of modern science still has many references to its Arabic roots. Take scientific terms like algebra, algorithm, alkali. I instantly recognize these words as Arabic. And these are at the very heart of what science does. There will be no modern mathematics or physics without algebra, no computers without algorithms, and no chemistry without alkalis. From the 12th to the 17th century, European scholars regularly refer to earlier Islamic texts. In fact, Arabic names crop up in many medieval European texts on subjects as varied as map-making, optics, and medicine. But I want to start with Al-Khwarizmi, because his work touches on a crucial aspect of all our lives today. It's thanks to Al-Khwarizmi that the European world realized that their way of doing arithmetic, which was still essentially based on Roman numerals, was hopelessly inefficient and downright clunky. In his book entitled The Hindu Art of Reckoning, he describes a revolutionary idea. You can represent any number you like with just 10 simple symbols. The idea of using just 10 symbols, the digits from 1 to 9 plus a symbol for 0, to represent all numbers from 1 to infinity was first developed by Indian mathematicians around the 6th century AD. And you can see the similarity between these numbers, in particular, for instance, the digits 2 and 3. If I tip this sideways, you can see now how they look like numbers 2 and 3. And what's powerful about these digits, this numerical system, is how it's simplified arithmetic calculations. But Al-Khwarizmi and his colleagues went further than just translating the Indian system into Arabic. They created the decimal point. This text, written a century after Khwarizmi, is by a man we know only as Al-Uqlidasi, where he showed how the decimal point is used for the very first time. He describes it by using a dash. Here are the digits 1, 7, 9, 6, 8, and you can see there's a small dash over the 9 indicating the decimal place. The idea of the decimal point is so familiar to us that it's hard to understand how people managed without it. But like all great science, it's blindingly obvious after it's been discovered. The story of numbers and the decimal point hints that even over 1,000 years ago, science was becoming much more global. Ideas were spreading, emerging out of India, Greece, even China, and cross-fertilizing. And looking on a map that shows where people lived 1,000 years ago gave me my first insight into why medieval Islam would play such an important role in the development of science. Now look at which city lies at the centre of the known world, a place where the widest range of peoples and ideas were bound to collide. The Abbasid caliphs had claimed their right to rule by declaring that they were directly related to the Prophet Muhammad, who had founded the new religion over 100 years earlier. But in that short time, the armies of Islam had conquered a vast territory. Starting in a small area around Medina, they moved rapidly out of the Arabian Peninsula and within a few decades had taken control of the Levant, North Africa, Spain and Persia.
I think one must bear in mind that this is an era in which people actually believed in God, and the dramatic successes of the Arabs as they poured out of Arabia was such that a lot of people did sort of observe and say they must have God on their side, this must be the true God. Some people did convert, or if they didn't convert, they did submit to Arab Muslim political control for that reason.
By the early 8th century, Islamic caliphs ruled a vast territory. And like most successful emperors, from Caesar to Napoleon, they understood that political power and scientific know-how go hand in hand. But with military and political success, the Islamic caliphs faced an inevitable problem. How do you sensibly govern a hugely diverse population? Although some of the empire had converted to Islam, they were still separated by huge distances and adhered to many different traditions and languages. In the 8th century AD, the empire's leader, the Caliph Abdul Malik, had to find a way of administering this mishmash of languages. Like all the great figures of the Islamic Empire, Abdul Malik lived in a culture without portraiture. All we have are later impressions of what he might have looked like. His solution was sweeping in scale and inadvertently laid the foundations of a scientific renaissance.
It was this Abdul Malik ibn Marwan who said, this bureaucratic chaos has to stop. We cannot continue to run a government and govern all of this span of land with this Tower of Babel languages. So he wanted to govern it with a uniform language. That uniform language, of course, he wanted to be able to understand it, so he demanded that it be in Arabic.
But the choice of Arabic as the common language of the empire went beyond administrative convenience. the decision had extra force and persuasiveness because Islam's holy book, the Quran, is in Arabic, and Muslims therefore consider Arabic to be the language of God. The words of the Quran are so sacred that its text hasn't changed in over 1400 years. By comparison, English has changed dramatically in just 700 years. To our ears, Chaucer is almost unintelligible, whereas any Quran can be understood by anyone who reads Arabic. Making copies of the Quran has always been a specialized and highly respected job since the foundation of Islam. Calligraphy expert Naif Scarf, who lives in the Syrian capital Damascus, writes for mosques and in madrasas all over the country. These are words he's found himself writing over and over again, words of great significance for Muslims. They're the opening line to each chapter in the Quran. Bism Illah ar-Rahman ar-Rahim, which means in the name of God, the most gracious and the most merciful. Arabic calligraphy was enforced on them because of the spread of Islam, because they were worried the meaning of the words in the Quran would be lost if it was read by people who don't speak Arabic. Then they wouldn't, not only would they misinterpret it, they just wouldn't be able to distinguish between different letters. So not only did they add dots on certain letters, they also added other little squiggly lines which changed the sound of vowels. And it was something that they put in place just to ensure that people were able to have the right pronunciation when they read the Quran. The consequences for science were immediate. Scholars from different lands who previously had no way of communicating now had a common language. And it was a language that was specially developed to be precise and unambiguous.
What this meant was the summoning into existence of a vast intellectual community where scholars from very different parts of the world could engage in dialogue, comparison, debate, argument, often very fierce argument, with each other. It was possible for scholars based in Cordoba in southern Spain to engage in literary and scientific debate with scholars from Baghdad or from Samarkand.
In the early 800s, the ruling elite of the Islamic Empire were pouring money into a truly ambitious project, which was global in scale and which was to have a profound impact on science. It was to scour the libraries of the world for scientific and philosophical manuscripts in any language: Greek, Syriac, Persian, and Sanskrit, bring them to the empire and translate them into Arabic. This became known as the translation movement.
Some sense of the extent of this activity, sort of between 750 and 950, somebody called An-Nadim, who wrote a list of sort of the intelligentsia of the Abbasid era, lists 70 translators. So it was quite a large cohort of people involved in translation, and obviously he only named the well-known. They could get up to 500 gold dinars a month, which is probably around $24,000, which is a huge sum of money for what they were doing. It was a very, very prestigious, well-paid, well-patronized activity.
They knew extremely well that writings could be forgotten or buried or burnt or destroyed, that cities could pass away. And what we see in Baghdad or Cairo or Samarkand is exactly the gathering together, translation, analysis, accumulation, storage, and preservation of material that they were well aware could be entirely lost forever.
And if there was one branch of knowledge that everyone, from the mighty caliph to the humble trader, wanted to preserve and enhance, it was medicine. These were, after all, times when few lived to old age. Writings from the time remind us that what we might consider a relatively minor infection today could be a death sentence. Religious teachings, then, were not just a source of comfort. They were a constant reminder that we should never give up. In the Hadith, which is the collected sayings of the Prophet Muhammad, it says, "Ma anzala Allahu da'an illa wa anzala lahu dawa'an," which means that God did not send down a disease without also sending down its cure. It's statements like this that lead Muslims, even today, to believe that cures for all diseases are out there somewhere, and that we need to search to find them.
What people don't realize is that the history of Islamic medicine is really the history of our medicine, because our medicine, the university medicine we used until the 19th century, it was based to a large extent on all these work of these Islamic physicians.
Islamic medicine built extensively on the foundations laid by the ancient Greeks. The most highly prized and among the first to be translated into Arabic were the medical manuscripts of the 3rd century Greek physician Galen. Galen believed that a healthy body was one in balance, a balance of 4 types of fluids called humours, which circulate through the body, and any one of which, if out of balance, would cause illness and a change of temperament. But Islam's most tangible contribution to medicine is less in its specific remedies and more in its overarching philosophy. It is, after all, a religion whose central idea is that we should feel compassion for our fellow humans. This is the Nur al-Din Hospital, the leading hospital of the Islamic Empire, built here in Damascus and now a museum.
This was built in the 1150s, 1154 I believe. One of the ideas which are stipulated in Islam is the idea to be charitable. And charity,
zakah, yes.
Exactly, and it's an obligation to give alms and stuff like that.
Yeah.
And so if you're a ruler or if you have a lot of money, what you could do is obviously...
You could really be charitable.
Charitable and set up like a nice hospital like this one.
Okay. And within the hospital, Islam actively encouraged a high degree of religious tolerance, something we take for granted in modern secular society.
The hospital was open to all communities, so you would have Christians, you would have Jews, Muslims obviously, maybe other denominations, both as patients and also as practitioners.
I mean, typically, how many physicians would there be?
Well, it depends. Well, like for certain hospitals, we hear figures of like 24 or 28 physicians. Yes, the physicians would do the rounds in the mornings, you see, do their prescriptions
that's the
and
sort
stuff
of thing
like that.
Hasn't changed over the ages, yeah. As a result of the translation movement, those physicians now became aware of the latest remedies from as far away as India and China. And as the new drugs filtered in from the rest of the world, hospitals started to set up a new kind of facility within their walls, the pharmacy. So this notion of a pharmacy in a hospital, is that a new innovation?
Well, the whole package, certainly, that's new. And what is interesting, if you look for innovation, like on the level of pharmacy, if you look at Baghdad or even Damascus, it's at this crossroad of cultures. So loads of new things come in, like musk, for instance, myrobalan. You have like Indian drugs. There's like an Indian pill, for instance, which is good against headaches and bad breath, but also gives you sexual appetite and stuff like that. So Here you have like a wonderful illustration. It appears that this is the first anatomical illustration in history. Like you see, it says adala, which means muscle. And so these are like the different muscles which move the eyelids.
So it was understood then that the muscles controlled the
absolutely,
the lens in the eye.
Yeah, and moved the eyelid and stuff like that. So the other thing which we have here, which is really nice, is I think we have some like ophthalmological instruments. For instance, it's a hook, could be used, for instance, like to kind of pull back your eyelid, that sort of thing. I mean, these instruments were very useful to the doctor.
Although these tools might look crude, eye surgery was one of Islamic medicine's great successes. One innovation was to improve an older technique for curing cataracts called couching, which in their hands had a success rate of over 60%.
In a living subject, the cornea would be clear and you'd be able to see the pupil clearly with the cataract sitting behind the pupil, the wide opacity. Cataract is the lens inside the eye, which sits behind the pupil. As with time, with age, the lens gets cloudier and cloudier, and that's what is referred to as a cataract. Would have attempted to go in just by the white of the eye, just at the edge where the cornea is. And then what they are attempting to do is to sweep around, trying to break all those ligaments of that lens and trying to get the lens to drop away from the pupil to allow more light to enter in through the pupil and to brighten the subject's vision.
But of course you haven't got the capacity to focus.
Oh yeah, you haven't got a lens now, so that was a big problem until people started compensating that with specs later on. They were trying to remove the cataract away from the visual axis.
They understood the anatomy of the eye.
Exactly. They had some understanding of the anatomy of the eye and, that the lens was behind the pupil and that's what was causing the visual loss.
One Islamic scholar, more than any other, embodies the synthesis of religion, faith and reason. His name was Ibn Sina, or Avicenna as he's known in the West. He was a polymath who clearly thrived in intellectual and courtly circles. In 1025, he completed this, Al-Qanun fil Tib, or the Canon of Medicine. In it, Ibn Sina collated and expanded on all that had gone before him, medical ideas from Greece to India, and turn them into a single work.
Oh, it's hugely important. I mean, there are a few books which are as important as the canon because what this encyclopedia does, it kind of, sweeps away everything else. It becomes a textbook. It supersedes a lot of other texts, and people even complain that, it's so good, it's so tightly organized, it's so easily accessible that people forget to read the Greek sources in Arabic translations. This whole first book, this is the first book, contains what we call the kulliyat, the general principles. So it's all about how the human body works, how diseases work in general. The second book contains diseases, what we sometimes call from tip to toe, from tip to toe. So he starts with the diseases of the head, and then he moves down like the eyes, the ears, the nose, the mouth, and normally they end up at the sexual organs, you see.
At first sight, the sheer ambition of the 3 volumes is hugely impressive. Here's an attempt at diagnosis and cure for diseases as diverse as depression, meningitis and smallpox. And there's even detailed chapters on more common problems.
So, for instance, here you have headaches.
So different kinds of headaches.
في العلاج الصداع الحادث عن الروائح الطيبة. So headaches caused by pleasant, fragrant smells.
And then he's also got الحادث من الخمار, so hangovers.
Different kinds of jima. You can get headache from sex.
Is that right?
Well, hasn't happened to me yet, but let's see. So, the treatment of headache caused by sex. ويجب لمن يعتريه ذلك عقب الجماع وبامتلاء أن يبدأ بالفast. So if somebody has or is befallen by, suffers from a headache after sex, and he also has a repletion, so he has too many superfluities or something like that, so يجب أن يبدأ بالفast. One has to first resort to venesection or bloodletting. ثم بالإسهال, and then you should use purging. In وجب كل واحد منهما. For both of them, bloodletting and purging are necessary.
Ibn Sina's Canon of Medicine is a landmark in the history of the subject. Although much of the medical science it espouses we know now to be terribly misguided, its value lies in accumulating the best knowledge in the world at the time into one accessible, organized text. The canon would give future generations something to rewrite.
That's right.
This is Saqqara, a necropolis or graveyard of the ancient pharaohs. Over a 10-acre site, it's a collection of burial chambers and step pyramids that were built in the 3rd millennium before Christ.
Well, that's probably the biggest revelation for me so far on my travels, that Egyptology didn't begin in the 19th century. Yet again, it seems that Islamic scholars actually cracked hieroglyphics, and they cracked it for strange reasons. They cracked it because they were interested in astrology and alchemy. But here is another example of this amazing translation movement. They weren't just translating Greek and Indian and Persian texts, they were translating Egyptian hieroglyphics as well. Absolutely incredible.
Unfortunately for the Caliph al-Ma'mun, the hieroglyphs contained no alchemical secrets. But what this story reveals to me is the insatiable curiosity Islamic scholars had about the world. They were desperate to absorb knowledge from all cultures purely on merit, with no qualms about the places or religions from which it came. But it's worth remembering that the translation movement wasn't just about science and medicine. As the capital Baghdad sat in the center of a vast, successful empire, it became home to an extraordinary flourishing of all kinds of culture. For this is the time described by 1001 Nights, of great and generous caliphs, magic carpets, great journeys, but also ambitious buildings, music, dance, storytellers and the arts. Baghdad was such a cultured and vibrant city that one traveller of the time wrote, "There is none more learned than their scholars, more cogent than their theologians, more poetic than their poets, or more reckless than their rakes." It really must have felt like Baghdad and the Arabic Empire were the world leaders in civilization and culture. To be part of that city's growing intellectual elite must have been as exciting as it gets.
It was a new Muslim city. It only started to be built in 756. So it has that sort of sense of almost being on a frontier, of being something new, of being something different. It was full of courtiers, it was full of sort of nouveau riche individuals who were trying to make their way at the Abbasid court. And it is the sort of a place, if you like, where innovation is valued and appreciated.
At the heart of the city's intellectual life was a system called the Majlis. Now the word Majlis could probably best be translated as salon or talking house. In 9th century Baghdad, what this meant was that the city's elite, the caliph, his courtiers, generals, and the aristocracy, would hold regular meetings, you might call them seminars or discussions, during which the city's cleverest men, the philosophers, theologians, astronomers, and logicians, would gather to discuss and debate their ideas.
It was not the case that people were expected to adhere to a particular line or adopt a particular religion. They were allowed to express their own sentiments and their own views very freely. The point was that they should do so in elegant Arabic and a good logical reasoning.
Out of the very heart of this intellectual whirlwind came Al-Khwarizmi, mathematician, astronomer, courtier, and favourite of the Caliph al-Ma'mun.
Al-Khwarizmi brought together two very different mathematical traditions and synthesized them into something new.
The capacity to have on your desk simultaneously two very different kinds of mathematics presses on models of what counts as calculation, what counts as measurement, and I think accelerates the process of intellectual change.
The first of these traditions came from the Greek-speaking world. Greek mathematics dealt mainly with geometry, the science of shapes like triangles, circles and polygons, and how to calculate area and volume. The other great mathematical tradition Al-Khwarizmi inherited came from India. They'd invented the 10-symbol decimal system, which made calculating much simpler.
Thanks to the translation movement, Al-Khwarizmi was in the astonishingly lucky position of having access to both Greek and Indian mathematical traditions. He was able to combine geometrical intuition with arithmetic precision, Greek pictures and Indian symbols, inspiring a new form of mathematical thinking that today we call algebra. I see here, although it's written sort of in the margin, the title of the book, Al-Jabr wal-Muqabala. So that's the first time the word al-Jabr appears.
Algebra.
Algebra, that's where our word algebra comes from. Now, what I found very early on is that he said, I discovered that people require three kinds of numbers. Judur wa amwal wa adad, so roots, squares and numbers. So what is he trying to do here?
This is what we would now call x and x squared. This is quadratic equations. This really is algebra. Root and square as if they're objects in their own right. They're not just some number that we're trying to find out. They're a process you apply. What Al-Khwarizmi is thinking of is square means take the root and multiply by itself. And that recipe is true whatever the root might be. If it's 5, it's 5 times 5, it's 25. If it's 3, it's 3 times 3. He's giving you a general recipe, now called an algorithm.
What is the true global importance of algebra? It's been used throughout the ages to solve all sorts of problems. Let the mass of the cannonball be m. Let the distance it has to travel be d. Use algebra to work out the optimum angle you have to point your cannon. That sort of knowledge wins wars. Or let's call the speed of light c, the change in mass of an atomic nucleus m, and then calculate the energy released with the following algebraic formula, E equals mc squared. Mastery of that information truly is power. Algebra has helped create the modern world. Our science is unimaginable without it. It sums up so much that was remarkable about medieval Islamic science, taking ideas from Greece and India, combining and enhancing them. Similarly, modern medicine owes a considerable debt to the work of the Islamic physicians. But I think the real story of what happened to science in the Islamic world in the 8th and 9th centuries tells us more than any single discovery. What it really tells us is about the universal truth of science itself.
Wealthy, powerful, successful cultures will produce enormous advances in understanding and in technique. And that's just what we find in Islam, in Baghdad, under a series of successful, powerful, wealthy, and self-confident Islamic regimes.
Over 1,000 years ago, the Islamic Empire was the largest in the world. It governed an estimated 60 million people. That was over 30% of the world's population.
These ancient walls, tucked behind a back street on the outskirts of southern Tehran, are literally all that remain of the ancient city of Ray, the city that the great Persian geographer Al-Muqaddasi described as one of the glories of Islam. Of course, Ray was just one of a number of cities that flourished under early Islamic rule. From Baghdad, its capital, the empire spread across thousands of miles, from North Africa through to Central Asia.
Think of that span of land. This is larger than any empire human civilization had ever known. Within that span of land, you can plug in the Roman Empire and it will fill just maybe, what, 1/3 of it, 1/2 of it, or something like that.
They did have a big and sophisticated governmental administration, and obviously that needed knowledge. If you wanted to be an administrator and you had to assess taxes, you needed to know about mathematics. It also wants to be able to build monumental buildings. That requires the knowledge of architecture and, again, mathematical skills to construct fine buildings safely. Medicine, just to keep the elite happy and healthy. And those are the areas with knowledge which are first translated from other languages into Arabic.
This is the mighty River Nile as it flows through the Egyptian capital, Cairo. Since antiquity, its unpredictable floods have determined the fate of Egypt's people, bringing years of lean and plenty. By the 8th century, Cairo was part of the Islamic Empire, and the new rulers took the first step to understanding this mighty river in a scientific way. They built a device to measure it. It's basically a huge colonnade that was built in a chamber connected by tunnels to the river. As the water rose or fell, its height could be read from the central column.
The central colonnade here is ultimately a measuring instrument. It is very precise. It's almost 1 inch between a marking and another.
Presumably they need to know seasonal variations in the height.
And to try to have some sort of record so that they could measure against certain years, where a year was known for a high level of flood versus another year known for its drought. Then they might perhaps take some precautions.
Yes.
The data collected from the Nilometer did have one practical use. By creating an objective record of the river's behavior, it allowed the rulers of the time to calculate how much tax to levy on Egypt's farmers. But whatever its uses, what I love about the Nilometer is how it shows that to understand the world, you have to build devices to measure it.
If you think very hard, it's never obvious that measurement can make sense of the world around us.
And one medieval Islamic ruler made measurement a personal obsession, giving it a scale and ambition that was truly unprecedented. His name was El-Ma'mun, and he became the caliph or ruler of the Islamic Empire in 813 AD. El-Ma'mun funded a range of scientific research, but one particular project was a personal favourite of his. And given that he ruled over such a large territory, it's hardly surprising what it was: map-making.
In the second decade of the 9th century AD, El-Ma'mun commissioned a new map of the world. And his scientists did a pretty impressive job. It was a vast improvement on all maps that had come before. What we see here is that they've really got the Mediterranean, its shape and how it links in with the Black Sea, the Middle East, even the whole of Asia as far as China and Japan. They've even got the Indian Ocean and the east coast of Africa. It all looks pretty impressive for the known world at the time. Of course, what El-Ma'mun ultimately wanted to know was how much of the earth as a whole did he possess? And this begged the question, just how big is the earth?
And more specifically, the practice of Islam demanded that its followers have a very clear idea of the size and shape of the world.
Now, this is crucial information for Muslims because wherever they are in the world, they need to know the direction to Mecca for their prayer. This is known as Al-Qibla. Now, over such a large territory, finding the direction to Mecca is not a trivial problem. This problem was wonderfully illustrated when a mosque was built recently in Washington, D.C. Some worshippers were confused because the direction they were told to face when praying was slightly north and not southeast as they expected. After all, Mecca is southeast of Washington, and on a flat map, it does appear to lie in that direction. But on a curved sphere, the shortest distance between any 2 points follows what's called a great circle. So, for example, this great circle line between Washington and Mecca is quite different to what you might expect. So the direction to Mecca from Washington actually points slightly northeast rather than southeast. Of course, this is complicated stuff, but the key point for Islamic scholars is that knowing the direction to Mecca requires a knowledge of how steeply the earth curves. And that means knowing how big it is. So Al-Ma'mun commissioned his very best scientists to measure it. Al-Ma'mun's astronomers repeated the Greek experiment in Syria and Iraq by measuring the angle of the sun in the sky at noon at one known location. They then walked due north to a second location, carefully measuring the distance they travelled. At the second location, they once again measured the angle of the sun at noon. This angle would have been slightly smaller than the first one. With these figures, Al-Ma'mun's astronomers were able to estimate the Earth's circumference. They got a value of 24,000 miles, within 4% of the correct value. Not bad, you might think, but this method was flawed and ultimately unreliable. A more reliable and sophisticated method for estimating the Earth's size was needed, and 2 centuries after Al-Ma'mun died, it came. What made it possible was a great leap of imagination, and the fact that by 900 AD, much of the world's mathematical knowledge had been translated into Arabic, so scholars could scrutinize and improve on it. Out of this obsession with scholarly learning came a true mathematical visionary, Abu Rayhan Muhammad ibn Ahmed al-Bayruni. And like all Islamic scholars of the time, al-Bayruni was obsessed with the science and mathematics of the ancient Greeks, Babylonians, and Indians. And because of the success of the translation movement, he had literally on his desk the great work on geometry by Euclid, Ptolemy's Almagest, the Indian text, the Sinhind, and the famous work on algebra by Al-Khwarizmi, which has as its 3 corners the mountaintop, the horizon, and the center of the earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the earth, and algebra allowed him to calculate it. With this formula, Bayruni is able to arrive at a value for the circumference of the earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%, a remarkable achievement for someone 1,000 years ago. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world. Einstein used precisely the same approach, admittedly with much more advanced mathematics, when he developed his general theory of relativity almost 1,000 years after Bayruni. But both Einstein and Bayruni were united by a single common idea. With mathematics, humanity can embrace the universe. By 700 AD, the Islamic Empire was taking the first steps towards mass production. And in this world where knowledge of materials, metals, and how they're worked became increasingly important, one practice flourished. It's the practice that was inextricably linked with magic. Specifically, the dream to turn base metals into gold. The mysterious practice of alchemy. The ancient art of alchemy was a mystical system of belief based on spells, symbols and magic. But I believe it took Islamic scholars to turn this quasi-religion into something much more scientific: chemistry. Increasingly, the knowledge of the alchemists found more and more practical applications. For instance, when, during the last decade of the 7th century, the ruler of the Islamic Empire, Abd al-Malik, made the bold decision to create a common currency for all his dominions, he turned to alchemists for help.
The proportion of gold to other alloyed metals that you have to put into the dinar to make the dinar usable. Otherwise, pure gold will become very soft and you can't use it. So that proportion is adjusted by, believe it or not, in this period, the alchemists. It is the alchemists who knew how to combine metals together and how to get the proportions of this gold to silver and gold to bronze and so on.
This is an Islamic dinar. The date of this it is 128 after Hijri.
So the middle of the 8th century, almost 740s.
Yeah, in the middle of the...
This 1300-year-old coin, made of an alloy of different metals, isn't just durable. It's also malleable enough to be inscribed with intricate Arabic writing.
No God instead of Allah.
Coin making is one of the many examples of how the practical needs of a booming economy began to turn the magical practice of alchemy into modern chemistry.
A great example of applied chemistry in the medieval Islamic world was the manufacture of soap. This stuff, solid soap that you can really clean yourself with, was virtually unknown in Northern Europe until the 13th century, when it started being imported from Islamic Spain and North Africa. By that time, the manufacture of soap in the Islamic world had become virtually industrialized. The town of Fez boasted some 27 different soap makers, and cities like Nablus, Damascus, and of course Aleppo became world-renowned for the quality of their soaps.
A 12th century document has the world's first detailed description of how to make soap. It mentions a key ingredient, and it's a substance that became crucial to modern chemistry, an alkali.
Now, alkaline substances are crucial to soap making, but what's interesting is that our word alkali derives from the Arabic al-qali, which means ashes. That's because back then, alkalis were manufactured from the ashes of the roots of certain plants like saltworts.
Islamic chemists' new understanding of alkalis and other new chemicals gave another industry a lift too: glass making. The Islamic chemists discovered that they could change the color of glass using newly discovered chemicals like manganese salts. And they built industrial furnaces, some several stories high, to manufacture glass in huge quantities. The legacy of their skills can still be seen in beautiful stained glass windows. Islamic chemists also developed many other colours, pigments and dyes, using their new alkalis and metals like lead and tin. These helped architects to decorate mosques, like this one in the Iranian city of Isfahan, in a glorious range of colours and designs. Perfumiers pushed chemists to come up with ever more ingenious techniques for extracting subtle and fragile fragrances from flowers and plants. They responded by refining and really establishing a technique that all chemists would instantly recognize today: distillation.
Distillations would have been done in devices sort of related to these. This is what's now called a retort, and we don't really use them anymore, but retort comes from the word to bend. In other words, a flask which has been bent over, and that's crucial. Well, many of the techniques...
The shape means that a gas produced in the flask is forced to condense in the spout, and it's the main way of extracting scents from flowers and plants.
Now, the idea here is that you heat at this end and you collect at the other. And so we should actually take a look and see if we can do a quick distillation with rose petals. First, we need to just put in a little bit of water. The water and steam will essentially control the temperature. What we don't want is for this to get too hot. Because
the trick with this kind of distillation is to use heat to release the scent molecules, but at the same time making sure that these delicate substances aren't destroyed in the process.
You actually use the steam to control the temperature, and the steam will carry those smells over. You can see the liquid coming up, condensing in the long tube. And there is already liquid coming over.
Through, yeah.
And that should be carrying with it some of the sort of rose water smell.
Historical records during the Crusades talk in terrified tones of how the Muslims would attack the Christians with burning missiles and grenades, striking fear into the hearts of the defenders. Many of these use a substance known as Greek fire. Islamic chemists improved on Greek fire by using and refining a naturally occurring resource, petroleum. They developed the idea of distilling petroleum, or naft, to create a lighter, extremely flammable oil, which they mixed with other volatile chemicals to make them burn furiously. And the result was clearly terrifying. This is the centerpiece of modern chemistry, the periodic table. It lists all the known elements. Its key idea is to group substances with similar properties together. On the far right, for instance, are the inert gases. On the far left are the volatile metals. The periodic table is a triumph of classification, giving scientists a way of organizing their knowledge of the material world. People have been trying to classify the material world since ancient times. The Greeks, for instance, thought there were just 4 worldly elements: air, earth, fire, and water. But this idea was a philosophical one and had little practical value. And that's what medieval Islamic chemists really changed. They used experimental observations to classify the stuff the world is made of. At the forefront of this was a medieval Islamic doctor and chemist called Ibn Zakaria al-Razi. Al-Razi's classification was very different from the Greek one. He argued, for instance, that minerals, roughly stuff we dig out of the ground, should be classified into 6 groups, depending on their observed chemical properties. The same guiding principle that lies behind the modern periodic table.
Now, what I've done is I've brought materials from his classification scheme. And we have here what he called the spirits. We have the metallic bodies, we have the stones, then we have the atriments, the salts, and finally the boraxes.
Each of al-Razi's groups had a profoundly different experimental behavior. For instance, spirits were flammable. The metals were shiny and malleable. Salts dissolved in water. Of course, these classifications are not the way we do it today. But the point is that for the first time, al-Razi was grouping substances on the basis of experimental observations, not philosophical musings. I believe that what we see in the work of the Islamic chemists and alchemists is the first tentative steps to a new science. Yes, by our standards, it contained a lot of magic and mumbo-jumbo, but it placed an emphasis on experimentation that was truly revolutionary.